Hello and welcome to Focus Hour Calculus. Today we'll be discussing the derivative, a brief overview of what exactly the definition of a derivative is, and then also going into the nitty-gritty, talking about the meaning, derivative notation, a brief mention of higher order derivatives, tangent lines, and also where exactly is a function differentiable and where is it not. We'll also be briefly mentioning the practical meaning of derivatives. So with that out of the way, let's begin. First and foremost, the most important question: what is a derivative? Or what are derivatives? Well, there's two definitions of derivatives, and those definitions can all come in useful in their very own times. But the most generic one, or the most common one that you will see throughout the wide world of math, is going to be this one. So this is going to be a limit notation as lim of h goes to 0. The function of f(x) plus h minus f of x over h. This is going to be a very, very important limit, and also the definition of a derivative. So whenever someone asks you for the definition, make sure to give this one. This is the basic one. But then there's also a more interesting one, and that's going to be the derivative at a point. And this one can be expressed also as a limit, but with x0 instead of h. So limit as x approaches a point x0 in the function f of x minus f of x0 as x minus x0 on the denominator. Now, you might be able to notice something with this specific limit, and it's that it oddly looks very much like the formula for finding slope, and you'll be absolutely right. As you can see here, this is one function, let's assume y1 minus y2, and this is x1 and x2. So this is very much similar to the formula of finding slope. The only difference is that rather than having two values, y1 and y2, x1 and x2, we instead have x be a specific value, but not represented as a value. It would just be a variable representing any value whatsoever. So then let's take a look at what these mean in word form. So first, the first definition of derivatives is the slope of a tangent line at a point. Slope of a tangent line at a point. And the second definition of derivatives is more simple: the instantaneous rate of change. Instantaneous rate of change. Both of these definitions work, but it's better explained through the first option. Let's see exactly why. So let's come out a bit, and then right here, I'm going to draw a graph. And this is going to be the graph of a parabola. This parabola has x, y, and all of these values. Now let's assume that in this parabola, there is a point A. The derivative of f of x, assume that this is f of x, at point A is equal to the tangent line, or the instantaneous rate of change, at point A. Now, in order to find that specific value, you need to follow the lines that has seen the slope. So as you can see, currently, if we follow only this point, the slope would be around here. But as you see that as we continuously get closer and closer to the point, let me just draw these, the line that intersects it kind of is able to dwindle down in its slope. It gets from very steep, as you can see right here, to not as steep, as you can see right here. Now let's take a look at the other side as well. The other side, let's just dot 3 points first. And let's take a look at the tangent line of those 3 points. Right now, it's very steep. As you can see, it seems like a very steep line that intersects as the tangent line. Right here, it's way less steep. It's very, very much still steep, but very, dwindled down a bit. And here, it is less steep. And as it goes from this more steep form to a less steep form, you kind of are able to foreshadow what exactly the tangent line of this point is. It slowly dwindles down in steepness until it becomes flat. And that is called a horizontal tangent line. Also known as a critical point. However, we'll get into that later. It's not a topic for now. So the tangent line is able to be seen throughout a single point. However, it may seem a little puzzling at first. You will get the hang of it, I'm pretty sure. But then let's also take a look at what derivative notation is. So in derivative notation, there's, I would say, two ways to express derivatives. So if you want to find the derivative of f of x, you are able to find it in the first way. Oops, I spelled it wrong. Derivative. And the number one way is using just very simple, a single punctuation mark. That is the derivative of fx expressed. You have this singular punctuation mark make the difference. And the second way you're able to express it is through something called d over d of x, of f of x. There's another way to express it that I would say is very useful. However, typically if you want to save work, you just use the first option. Now, you can see that this isn't a way of expressing derivatives, but what about something called higher order derivatives? We won't be getting into that right now, but what if, let's say, we want to find the derivative of something that has already been derived? So for example, let's find the derivative of f prime x. We call it prime. What is the derivative of f prime x? Now, in this case, the derivative of f prime x would simply be another prime. F double prime x. In the case of dx, d over dx, we do d squared y over dx squared of fx. And that is how you express higher order derivatives. Okay, since we understand that, let's go back and do a few problems then. Well, before that, actually, let's consider where exactly do derivatives exist. So, how is a function differentiable? Exist. Now, there's two requirements in order for a derivative to exist. First, the function must be continuous. And second, the function of the slope just before the point is equal to the slope after. Okay, so this may seem a little confusing, so let's do the complete opposite right now. Let's ask a different question. Where do derivatives not exist? Well, to answer that, we just have to do the exact opposite. First, let's come out and see the requirements. It has to be continuous. Okay, so when is a function not continuous? Let's just name a few examples. The first exception to differentiability is a vertical asymptote. It's pretty simple. If you have a function, let me just draw a function real quick, that has a vertical asymptote, that means that they're not going to be connected. And given that, they're probably not continuous, therefore not meeting that requirement. That, I would say, intuitively makes sense. And then there's also the second one, which is a hole. If you have a function that just simply dwindles out at one point and then continues, you're not going to have a good continuous function. You're going to have something that is not continuous. Okay, what is another example of a non-continuous function? Third one is going to be a jump. Well, it's similar to a hole, but it's not exactly connected. So for example, it's going to be this, a hole, but instead of here, it's going to start off here. That's going to be a jump. That's also not continuous. Okay, so other than that, let's take a look at the second one for one. The slope before has to be equal to the slope after. What exactly does this mean? So I'll give you two graphs and you tell me which one meets that requirement. So here, the second one. Sorry, it's a little ununiform, but this is the best I can do. So the first one is this graph. Second one is this graph. Tell me option A or option B. Which one meets the requirement that a slope before is equal to the slope after? It's option A. That's not right. Okay, so let's talk about exactly why. So in option B, the slope before and the slope after are pretty much the same. Yes, it slowly changes as we've discussed before. The tangent line is slowly getting less steep as you continue. However, it's going at a gradual process. On the other hand, right here, you're not going at a gradual process at all. While the tangent line is currently like pointing downwards, being negative, it suddenly goes to this side. So it's very much changing. And that's because, and that's exactly what makes it, at this point, assuming it's point A, not differentiable. And therefore, our fourth exception is going to be what we call a cusp. And mainly, cusps are seen when there is an absolute value. Because that's just how it works. What's the fifth exception? Now, the fifth exception is going to be something similar, but not as much. It's going to be what we call a corner. Now, a corner is similar to a cusp, but not a cusp, and that's going to be when you have something like this. This is a corner. When you have a line or any type of straight line paired up with a curve, you're going to be able to see a corner. And seeing as, once again, the slope before is not equal to the slope after, you're not going to have a differentiable function because it doesn't meet the second requirement. Therefore, corner is the fifth exception. We also have a sixth exception. And the sixth exception is what we call vertical lines. So when we have vertical lines, just move here for a second, you're going to have a slope. So for example, we understand that any vertical line right here has no slope. And this isn't just saying slope is 0, this is saying m does not exist. Therefore, you're not going to be able to find a tangent line or an instantaneous rate of change when the rate of change doesn't exist. So for that reason, the sixth one is going to be a vertical line. Now, you might be thinking, we're not usually getting questions with a complete vertical line function, so why is that relevant? Now, the reason why this is relevant is because sometimes functions have vertical lines or vertical tangent lines baked within them. So for example, let's assume a function that looks like this. Yes, it might look like a normal function, and that's a bad drawing, so I'm going to make it better. But this point might have a vertical tangent line. And until we are told that it does not, we have to assume the possibility that it is. And therefore, we can say that a function at, let's assume, point A is simply not differentiable. But the seventh and last exception is an endpoint. So once again, let's take a look at our second requirement. The slope before has to be equal to the slope after. If I simply have a point that does not end, whoops, that was a mess, a point that does not continue, this point solely has a singular slope going this way, but none that reciprocates it and comes back. Therefore, the slope after does not exist unless this one does not exist either, to which there is no function at all. You're not going to be able to see any amount of derivatives or tangent lines being placed. So for that reason, the seventh one is going to be an endpoint. Now, we've gone over all that. Let's take it to the last item on our agenda, and that is, what is the practical meaning of derivatives? Now, this isn't usually discussed, but this is going to be on if you're taking and planning to take Calc AB or AP Calc BC. This is going to be a topic that could be on the test, so I do advise to keep careful, even though it isn't normally very commonly discussed. Normally, the practical mean of derivative, let me just draw a graph. So you mean that this is the graph f of x, y, graph f of x, and we're trying to find the derivative at point A. In this case, we're able to find the tangent line at any point one item away. So as long as we're able to find the change by one unit away from x, that is the practical value of a derivative. So once again, if you're given a word problem or some problem that asks you to find the derivative through practical meaning or some practical purpose, you are able to find it through this way. Once again, and it's pretty important, it is the change of y by 1 unit of x. So here, that would be a plus 1 and a minus 1. I forgot the plus. Let me just add that here. And that's the practical meaning. And that's it for derivatives. Thank you for tuning in.